sharp.
Hello, everyone. Yeah. First, I want to thank you for the nice keynote, and then we will have our first paper presentation. First paper is a tech-driven test case generation approach using model checking technique for collaborating systems. This will be presented by Blaise Miholet. He is a PhD student at KAIST, and his research topic focused on design and development of SOS behavior. SOS is a system of systems, behavior-aware collaboration using a policy-driven decision-making approach. So let's welcome the first speaker, Jalarem. So could you start your presentation?
Okay. Thank you so much for the brief introduction. Hello, everyone. My name is Zalala Meret, and my colleague in this work is Lingjun Liu. So I would be presenting our paper titled Attack-Driven Test Case Generation Approach using model checking technique for collaborating systems. So it's very interesting that the keynote speech today by Mahdi Miracorli presented about secure by design, and it contains a lot of information that can support our arguments for our workers. So, for example, in the EQE fixed cyber attack case and the colonial pipeline, CNA, financials, all these aspects of cyber attacks that causes economic losses for different companies is also one of the motivation to think about designing a test case generation approach for model checking techniques. So I will start my presentation now. So my presentation content looks like this. I would have a little bit introduction, overview and related workers, and overall process, models and model checking, counterexamples to test case conversions that the algorithms we have designed. And I would also discuss about test case evaluation and some future work. So I will give detailed discussions about each of these contents in the upcoming slides. So cyber attack, basically, with the popularity of cloud computing systems and network connected systems, there are more ways of attacking organization. And the details of these attacks is also presented in the keynote speech, Secure by Design. Cyber attacks have become more sophisticated, elusive, and targeted, particularly than ever. And the effect of cyber attacks on critical infrastructure can be more severe and ranges to disruptions of basic services. For example, in 2019, these are few of the reports of cyber attacks on critical infrastructures. For example, commercial aircraft business information system, and the electricity provider in the city of Johannesburg suffered serious disruptions after a ransomware attack. And I mean, the details have also been discussed in the first in the keynote speech. Then American Medical Collection Agency major data breach exposing personal and payment information, and the list goes on. Even in a single year, there are so many cyber attacks posed on different organizations. Apparently, cyber attack reports only shows what has been officially reported from victims. However, it's obvious that there are several other cyber attacks which are not reported, mainly because of privacy of the organization or the reputation of the organization. And several others also exist but not discovered. Now, is there any opportunity from the cyber attack reports, already known and publicly available reports? And how can we make use of this information to our advantage in terms of securing our systems? So with these motivations and curiosity questions, we observed these three important elements. For example, more information about cyber attacker behaviors using cyber attack reports can give insights about the state of the cyber attacks. And based on that, we can design the security of our systems. And the organized information about type of possible attacks and attack targets, attack scenarios, which forms the putative attacks for a specific domain, also provide us information about how to make our systems more secured, which is also the result of the cyber attack reporters. And last but not least, cyber attack trends can be projected based on the cyber attack reports collected from different domains and also for specific domains. For example, in the air traffic control domain, there are well-organized information, not, for example, including about the methods of the cyber attacks and also the vulnerability of the system here, particularly on the ADSB protocol, and also the complexity of the attacks and the severity the attack can cause for that specific domain. So this kind of information can provide organized or putative information for the specific domain that we can exploit it to design a more secured system. So now dealing with a cyber attack requires a systematic approach, and on top of the existing attack defense orientation. So in this regard, testing is one of the well-recognized approach for identifying cyber attacks and also any other type of attacks. But the problem is test design has different challenges. For example, choosing input values, generating sequence of operation calls, generating executable test cases that include verdict information to verify whether the system behaves accordingly or not. And on top of this, the case becomes more complex when we consider complex systems, such as system of systems or the collaborations of different autonomous systems. Broadly speaking, testing can be divided into two, white box testing and black box testing. And model-based testing is a black box testing, mainly for functional testing and test case generation approaches. So it relies on three main methods of designing test cases and generating test cases. These are domain model, environment models, and system behavior models. Or it can use the hybrid of these two or three of them in order to design test cases and generate test cases for the system under test. Now, what is common in these three methods is they all rely on collecting information about the system, whether internal or external to the system. And then based on that information, they tried to design test cases for the system under test. And then how about attack behavior model? Because the attack behavior model also provides information about the system, and particularly it provides information about the security of the system or the vulnerability of the system. So in this work, what we are trying to do is exploiting this opportunity to design a better test case in order to secure our systems based on the attacker behavior model. So this takes us into the motivation and goal statement, identifying cyber attack vulnerabilities of software systems that can result in implementation flaws or overlooked constraints at or during design time. In the motivation, there could be overlooked constraints or flaws in programming that can be used by the attackers in order to attack the system. So how can we identify these vulnerabilities at design time? That is the motivation of the system. Our approach, our work. And then the goal is a model-based approach to cyber attack vulnerability analysis using focused test case generated based on putative cyber attack models. So we would be focusing on putative cyber attacks, which are organized information about the specific domain, and then we would be utilizing this information to generate test cases based on the focused approach. So with this, let me give a little information about the literature reviews that we have conducted, and two important points that we have observed from the literature reviews. In the model-based testing, test case generation, many of the workers focuses or utilizes these three methods, as I tried to give briefly in the previous slides: domain model, environment model, and system behavior model. The limitation in the domain model and the environment model is they rely on the external information of the system, so they cannot specify expected outputs because they do not have a means to discover the behavior of the system internally. However, they can be used in a sophisticated way to design test cases and then mix testing on the systems. The system behavior model relies on the behavior of the system, different components, behaviors of the system, and then based on that behavior of the system, then the tests can be designed and they can be generated. So it includes a verdict information to make sure whether the tests achieves their goal or not based on the system behaviors. Another observation that we have obtained in the literature's part is what are the techniques and or the common techniques used in the critical systems or safety critical systems to design test cases, which are the model checking is popular to design test cases for safety critical systems. And this only shows a very few research works, but we have investigated a lot more in our paper. Then you can also visit our papers to see more details about how the model checking is used to safety critical systems. Now, the overall process in our approach is it relies on the model checking techniques. So we need to have the system model and also the security properties to be checked or to be verified. What we have added in this well-recognized approach is we have added the attacker behavior model into the system, and then this behavior model can also make differences in the system model and the security properties, and then it generates the counterexamples. So we run a model checker called PAT actually. We used PAT model checker to generate these counterexamples. The counterexamples could be in different forms, in textual forms or in diagram forms, in different forms. And the counterexample actually contains parameter values and states and state transitions. So we devised an algorithm to trace the counterexamples in order to identify which states contain relevant information for test case design. So I would be discussing as well the algorithm that we have defined to convert counterexamples into test cases, because counterexamples cannot directly be used as a test case because it contains more model checking elements, including states, state transitions, and some parameters. So for that purpose, we defined an algorithms to convert counterexamples into test cases with such a template, like preconditions, test steps, test data, and expected results. And then we have the test case. Another part of our process is to simulate testing. For that purpose, we use JADE, a simulator, which is Java Agent Development Environment, in order to specify the systems and also in order to simulate the behaviors by using the test cases we have generated from the counterexamples. So this is the whole process that we have demonstrated in our paper, and I would be giving some detailed information. Air traffic control system obviously is very complex systems, and it has different systems connected to each other, and it's not possible to represent the ATC system as a whole. but we have selected a few systems in order for our investigation. So we have identified three relevant systems in the ATC, including surveillance data processing system and short-term conflict alert system, and also the flight desk, which contains the softwares embedded in the aircrafts. And we have analyzed what are the informations communicated between these systems and the protocols used for communication and the vulnerabilities of the protocols. And then we tried to represent each systems and their interactions and the messages communicated between them. So this picture, I mean, this model only represents the selected system components in the air traffic control systems. But it is typically shows how complex the system is. And from that higher level view, we also designed a flow diagram in order to understand how the parameters and the variables, the decisions each systems make based on based on our investigation from different sources. So, for example, in the surveillance data processing flow diagrams, we have decisions to check whether the runway is available or not. We have also the decisions to check requests list and check action reports. This is typically what the surveillance data processing system use for checking, I mean, as a data flow diagram to represent the system. And we have also the respectively for the flight desk system and also for the short-term conflict alert as a case for the security systems. And we represented how internally these systems are, and actually this is also an abstraction, so it represents only for components and their connections, data flows for security purposes. Then property specification and verification. So what we did is we specify the properties to be verified using the LETL specification format. And this is also possible on the path model checker. We also designed the system using the system specification using CSP language in order to define, for example, as you can see here, there is a system called system with intruder, and there is also an aircraft system, and there is also SDP and STCA, and then the intruder. All these systems are well specified with a little scope actually, and only focusing on the security aspect of the system. Then we run the model checker to see whether these specific properties, and this specific property is actually representing whether collusion exists or not in the system. So we can get verification results. And in these verification results, we have a counterexamples represented diagrammatically in this format that shows states, state transitions, and also it contains parameters and values of each states and the changes of the parameters and the values when the states are transiting from one to another one. So this is the models that we have experimented for the ATC system. And after generating the counterexamples, we have an algorithm, and this algorithm is used to convert counterexamples into test cases. And basically what this algorithm does is it tries to identify which state contains the attacker action. And whenever it finds a state that contains the attacker action, it traces back to the previous state and it gathers the parameters and the values of the previous state. And that would be used to formulate the preconditions of the system. And it loops throughout the counterexamples and collect all state that contains the attack actions and the previous state that comes to the state that contains the attack actions. And then it extracts all relevant information in the previous state that can be considered as a precondition. So with these algorithms, we were able to identify as described in the template, what are the preconditions for the attacker actions to happen. So based on that, we have this counterexample as an example, and these are the parameters and their values in each state, and these are the states or the actions performed by the system. So we have the attack actions and other actions involved. And so based using the algorithm that we have designed, we extracted all preconditions and then what changes can cause to the attacker actions to happen in the system. So by that, we were able to identify the vulnerability of the system by considering the attacker actions in the system. Then this could be the preconditions and then the test inputs and then the expected responses, because we are dealing with the behavior of the system. So it's also possible to know how the system behavior reacts to the attacker actions introduced. Then once we know this precondition, these preconditions might be the starting point for hidden vulnerabilities. Then we tried to provide different information based on these preconditions and see if there is a vulnerability of the system, hidden vulnerability of the system. For test case evaluations, after generating the test case from the counterexamples, we first simulate, design a model for simulation using JADE that includes the surveillance data processing, the flight disk, and the short-term conflict alert system. We designed their interaction using the simulator. And with this simulation, what we did is we have a test agent that monitors if test precondition is satisfied, as we have identified in the system. And then we provide some input test data that can reveal hidden vulnerabilities of this precondition. And then the test agent would monitor if expected results are satisfied or not. By doing this kind of simulations in a very scope down experimentation, we were able to identify there was a possibilities of collisions in our system by using the test cases generated from the counterexample. As a summary, what we did is we present an approach to discover hidden vulnerabilities based on known attacker behavior. And to do that, we considered putative attacker behavior as input models for model checking. And we use counterexamples to test case transformations. For future work, we are considering collaboration testing in the case of system of systems. So we have unit testing and component testing, integration testing, then system testing, which mainly focuses on a single system. But we are also trying to look at the possibility of collaboration testing or SOS testing based on the collaboration systems. And counterexample for focused monitoring, runtime monitoring using counterexamples sequences is also one of the future work to consider. So with that, I wrap up my presentation. If you have any questions, you are welcome.
Okay, thanks for the talk, JADE. Do you have any question? Actually, people didn't leave the question in the chat room. If you have any question, please leave the question in the chat room, or you can discuss with the presenters in the discussion room. I have a few questions. Among many model checkers, you utilized one model checker path. Is there any reason to pick the path, and are there any advantages or disadvantages of that model checker in your usage?
That's very good questions. Yes, of course, as you mentioned, there are several types of model checker, but we choose path model checker. One path model checker provides support to add external programs like C# or C++ in order to program complex systems. For model checking, because model checking usually does not support very complex iterative processes. But in the case of complex systems that we are dealing with, there are behaviors that need to be modeled with complex behaviors. So we choose path in order to model complex behaviors of the system, which has iteratives and loops that can be developed by using external packages like C# or C++ for more efficiency. That is one reason to use path, and another one is in paths model checker. We have different counterexamples representation, including textual representation and also graphical representation, and we can easily trace and observe the changes of the parameters and the parameter values on different states and state transitions. I think that is the very reason we use path model checker.
Okay, thank you. And one more is that which text scenario did you focus on? Maybe you already explained a bit, but what was the main security property that was verified in your case study? Can you elaborate a bit more?
In the paper, actually, we have a detailed description about the attacks, but just to give a highlight, we have fault data injections, and we tried to inject false data into the systems, and then that false data can cause decision problems of the collaborating systems. So particularly what we did is, because the major vulnerability in ATC systems, especially in aircraft communication, is the ADS-B protocol, which does not support authenticity, authorizations, and for that reason, data can be breached or data can be changed externally. So we use false data information to be communicated to the aircrafters. And that is the attacks that we tried to model in our system.
Okay, thank you. Do you have any plan to increase the type of attack scenarios in the future world?
Yeah, we are still we are still working on this topic, and we have a plan also to extend the work for more extensive ones by including different attack scenarios, and by actually also including different systems, that different component systems that would mimic the real environment of the application domain. So yes, still we are considering to scope up or to increase our experimentation so that it can be a representative one in the application domain. Yeah. Yes.
Okay, thank you very much. Now, we can close this presentation. So thank you for your presentation again. And then if anyone have any questions or comments, then you can go to the discussion room for this paper presentation. So thank you. And then the next paper presentation will start after 10 minutes. So we will have a 10-minute break. So see you after 10 minutes.
Okay, thank you. Thank you.
Now, backstage is again live, right? Currently, I found that in the continuous session, yeah, it's okay to just move from the